Hello everyone, my name is Motiejus Valiunas, and today I'm going to tell you about how mathematics can be used to study objects in high dimensions and what can we say about symmetries of things, and I will talk a bit about application to viruses as well. So on this lecture, I'm going to tell you a bit about symmetries on a plane, so what kind of symmetric objects we can have, and how we can describe them mathematically. In the second part of the talk, I will say something about how we can study similar things but in higher dimensions. So even in dimensions 4 and 5 and 6, we can have symmetric objects which we can describe, and we can study them. And in the end, I'm going to tell you about how we can use everything that I said to build nested structures which look nice, and how we can study viruses with these things as well. Okay, so let's start with symmetries. So we start with symmetries on a plane, which is just a two-dimensional object, so just a flat thing. And a symmetry basically is just a transformation that does not change distances, that does not change angles or sizes. So just if you have a flat object, you can move it around, but you cannot like stretch it or do something like that. Okay, so what kind of symmetries we can have? So there are three main types of symmetries. Translation is the first of them, and this is just to move things around without changing the orientation, without changing the way thing is presented. So if you have something that you can has top and bottom, then you can see that this top and bottom doesn't change. We just move it. On the other hand, we can have rotation, in which we could put a finger on the plane. So say we have a drawing on a table, a drawing placed on the table. So we can just put a finger in this drawing and then rotate around this around the finger to get transformation, which looks something like this. And the third type probably that I wanted to tell you about is reflection. So that is just flipping the object. So we can think about having a transparent film and with something written on this film, so we can flip it over to have it facing the other way, and that would be transformation presented here as reflection. So these are three main types, but what we want to study indeed in mathematics is we want to study objects which do not change when we do these kind of things. So our main first question now is, what kind of objects do not change when we apply certain symmetries to them? So I will talk a bit about finite objects and a bit about infinite objects. So let's start with symmetries of the second two types, so which are rotations and reflections. And this can be, there are finite objects which do not change when we apply rotations and reflections. So what's an example of such thing? So we have symmetric shapes, which are in very symmetric finite shapes, which are invariant under reflections or rotations. The simplest example of such thing is a regular polygon. So we can have like a triangle or a square or something like that. And so what kind of so there, we cannot have any rotation or any reflection of these things, but we can have some of them. So for instance, if you have a pentagon, so that's just a polygon with 5 vertices, we can rotate it 1/5 of the way around. So that's what we can see in the blue arrow. And we can also say flip it over like this on the plane. Square is also a similar situation. So we can rotate it now 1/4 of a turn, so by 90 degrees, or we can just flip it over, and either it's reflection in a diagonal where we just keep the diagonal in place and flip it over like this, or we have just like more usual problem, more regular flipping over, so just flipping it over in this axis. So that's what we study in mathematics. That's what I study in my work. In particular, I study objects which are called groups. So this is just a mathematical description of how we can describe the symmetries of things. Now that's about finite objects, but what about infinite objects? So we can have objects called lattices, and it is a periodic arrangement. So arrangement that does not change when you shift it in one or the other direction. So when you have a translation, so this can be described just as points where lines on some grid cross each other. So here are some examples. So the most usual grid probably you can think of, the most common grid you can think of is just a square grid here on the top left. We can stretch it a bit and deform it to have another grid, which doesn't look that regular, maybe that nice. Or we can have a grid consisting of the triangles, like at the bottom. So when we study lattices, we want to study the points of intersections of lines in this grid. So these blue dots are what is called a lattice, or these black dots. Yeah, we can just remove the line to see what kind of arrangements we can have. So these type of arrangements, they are invariant. They do not change when we do translation. So for instance, we can take this square lattice and just move this point over here to this point over here. But they can also be have some other symmetries. And what we are trying to do, we're trying to combine the symmetries you saw before with the polygons with the symmetries you see here with the lattices, which are just translating. So what can we have? So our question now is, given a polygon, is there some two-dimensional lattice, this grid of points, with the same symmetry? So we don't care that much about what kind of object we study, but we care about what symmetries it has. So for a square, the answer is yes. As we saw before, we have the grid like this, which is a square grid, and it has the same symmetries as a square, so we can also flip it over and it doesn't change. We can rotate it by 90 degrees and it doesn't change. So for a square, we can combine these symmetries. For a triangle, again, we saw the other grid, and we can rotate it now by 120 degrees, 1/3 of the turn, or we can flip it over, and again, it doesn't change. So we have triangles are nice in this respect. But what about things like a pentagon? So at first you may think, well, maybe we can find some arrangement of points on a plane that a pentagon will have symmetries, and it doesn't change the pentagons. The symmetries of the pentagon doesn't change your object. But in the end, it turns out that we can't have anything like that. So to have some sort of nice arrangements with symmetries of a pentagon, we need to do some other constructions. And that's what we're trying to see, what we're trying to achieve. So now let's look at what's the situation in higher dimensions. So in 3 dimensions, so what you think about as a space where you live, where you can not only move left, right, or up, down, but also we can go forward and backward. In this 3-dimensional space, you have polyhedra, and a polyhedron is basically just a 3-dimensional version of a polygon. So now you have something like a cube. That's a simple example of a polyhedron. And you can see, again, cube has some certain symmetries. So for instance, you can take a midpoints of 2 faces and just rotate it 1/4 of a turn. And if you have a cube next to you, like a Rubik's Cube or something like that, you can see that this doesn't change apart from the colors maybe. Or you can rotate it 1/3 of a turn when you pick 2 opposite points on the cube, 2 opposite vertices, and just rotate it 1/3 of the turn. Or you can also, in 3 dimensions, you can reflect. So you can flip it over. Well, in this case, it's not that easy because there's not that much space to move, so that you can imagine reflection as flipping it over, but you can just imagine the left and the right faces of the cube just changing places. So just doing something like moving one to the other. And another example of a polyhedron that I wanted to tell you about is an icosahedron. So this is a bit more complicated. It has 20 triangles, 20 triangular faces arranged in this way. And again, it has various symmetries. So for instance, you can pick 2 of these triangular faces and just rotate around them by 120 degrees. So that's 1/3 of the full turn. And again, you get what you started with. Or you can pick just two vertices, 2 opposite points in your polyhedron, and rotate it 1/5 of that turn by 72 degrees, as written here, and you have the same thing. So again, the same as in 2 dimensions, the same question arises. We have something that's invariant under rotations and reflections, but what about translations? Can we have something in 3 dimensions that you move it, you shift it to somewhere, and it stays the same? And the answer now is yes, that we can have a 3-dimensional lattice, which is the same as 2-dimensional lattice, basically. It is some periodic arrangement of points. So you can draw a grid in 3 dimensions. Maybe it's a bit harder to imagine, but you can draw a grid something like this. Just imagine continuing to infinity. And then in this case, you can move things in three directions, so that doesn't change. So if you move something one unit left, so 1 unit right, it doesn't change. Or you move it 1 unit up, it doesn't change. And you can also move forwards and backwards. And here you can see again that this big infinite object is associated to a small thing, which is a cube. So this in addition to moving to translating your lattice, you can also have all symmetries of a cube in here. So cube is good in this respect, that we don't need to do anything else. We already have, we already can see cube as in some big infinite object, which has the properties that we are trying to see. But what about something like icosahedron that you saw before? It's another polyhedron. So could we have some three-dimensional arrangement such that we shift it and doesn't change? And in addition, it has the symmetry of the icosahedron. So here, it turns out that it's not that easy. So in particular, we have a pentagon here on the icosahedron, and this is basically what ruins things in 2 dimensions. So in 2 dimensions, we saw that we couldn't have any lattice with symmetries of a pentagon. In 3 dimensions, it turns out that it's exactly the same situation, that the pentagon somehow restricting us, so we cannot have anything bad. So in particular, the rotation of 1/5 of the turn around two opposite vertices of icosahedron, this rotation is what ruins things, and we cannot have a three-dimensional lattice with the same symmetries of icosahedron. Okay, so now the question is, okay, we look at something like a pentagon, and we saw that in 2 dimensions, you cannot have any infinite arrangement that is symmetric on the translations and the symmetries of a pentagon. In 3 dimensions, it's the same thing, that we cannot have anything like that. So what if we just keep adding dimensions? Then what happens? So first of all, we need to define things. So it's not that easy to see things now that we cannot draw them, but in mathematics, using mathematics, we can describe things and describe the same things that we saw in the pictures in the 2 and 3 dimensions. We can describe it in any dimension we want. So we can describe in particular what it means for a lattice to exist. So again, we don't have any picture, but we can see, we can use mathematics to describe how it looks. And you can describe also something called polytopes, which are a generalization of polygons and polyhedra. And these again exist in any dimension. And what our aim is, our aim is to find finite objects that have the same symmetry as some lattice. So in particular, these symmetries of if you have a finite object, some polytope in this case, and has a symmetry of a lattice, then we call symmetries of this polytope crystallographic. And the name comes from things, the name comes from the word crystal. So if you take something like one of these rings, one of these 3 things, and so here you can see a diamond, pyrite, and a quartz. These 3 crystals, when you look at these things under a microscope, what you actually see is a lattice, a 3-dimensional lattice that I described above. So here, even in the middle picture, you can see that this minerals have like nice structure. They look like cubes. So it's because when you look at it close together, at how the atoms are arranged, then you can see that they are arranged very regularly, like points in a lattice. So this is where name crystallographic comes from. And now we want to see which symmetries, if we add more dimensions, well, what can we have? So for a pentagon, we saw that there's no there's no symmetries, there's no translations such that there's no lattice that is invariant under some translations and also invariant under symmetries of the pentagon. So we saw there's no such thing in 2 dimensions and there's no such thing in 3 dimensions. But in 4 dimensions, turns out that if you add a fourth dimension, a fourth axis to your coordinates, then you can have symmetries of the pentagon realized there in some sort of object. Or in case of icosahedron, which because icosahedron, as you saw, has not only symmetries of a pentagon, it also has 1/3 of a current symmetries of a triangle. It has more things. So 4 dimensions aren't not enough, but 6 dimensions, it turns out that 6 is the number that we need to go. So can have symmetric object in 6 dimensions, which has the same symmetries as an icosahedron. Okay, so we can describe these things. We can describe it all we want, but the question is, how do we see these things? So imagine we have some 4-dimensional object with symmetries of a pentagon. How do we see that it actually has symmetries of a pentagon if we cannot draw this? And the answer to that is we use something called a projection. So we can think about them as shadows from a higher dimension. So the same way you can think about shadows as an example to make 3-dimensional object into something 2-dimensional. So when the sun shines and you see your shadow, it is 2-dimensional. So we have something like this. For instance, so here's an icosahedron again, and it has so it has 12 vertices in total. So we can think about these vertices in here. In the outer, in the outer part of the drawing, we have 6 vertices which form a hexagon, and in the inner part of the drawing, you have 3 vertices that you can see, and 3 behind here you cannot see, but there are 3 vertices as well. So when you take a shadow of this thing, what happens is you just see a 2-dimensional thing, what we call a projection, and it's just a 2-dimensional hexagon in the outer part, and then another hexagon in the inner part. And this basically tells us that if we take our higher dimensional thing and project it down, we have some nested structure. So these are 2 hexagons, but the one is sitting inside each other. So it's like we can have like some sort of onion structure where layers are nested. So when going from 2 dimensions to 1 dimensions, I can show you maybe more precisely what we are doing. So we take a symmetric arrangement like this lattice in 2 dimensions. So we have lattices in 2 dimensions. And we can take some symmetric arrangement in here. So for instance, here I took an octagon, which has the same symmetries as a square, if you imagine a smaller square sitting here. So it has some symmetries. And now suppose we have some line, so that's a 1-dimensional thing. So we have a line going here in the middle, and we want to show what happens when we go from 2 dimensions to 1 dimension. So what the projection does is basically takes every blue point and moves it to a red point here that is closest to it on this line. And we have some sort of 1-dimensional arrangement. Now you can see on the line, we have just 8 points but there is some symmetry still preserved here. So for instance, we can take this point over here and flip the line over around this point. And then this will not change, the arrangement will not change. So we somehow had symmetries of a square, now we have less symmetries, but we have fewer dimensions. And when we take really high dimensions, like 4 and 5 and 6, this allows us to maybe not to see the whole picture, but to see some shadow in 2 or 3 dimensions that we can then draw, and we can see how it looks like. So here's what we get in case of pentagons. So we take some symmetric arrangement in 4-dimensional lattice. It contains a bunch of points, and then we project it down to some 2 dimensions. And when we do this, we can see that we can see some sort of nested structure. So different layers here of the structure are represented in different colors. So we have some points on the outside, some points in the inside, some points in the middle. And it has symmetries of a pentagon. So you can see that, for instance, if you take this arrangement and rotate it by 72 degrees, 1/5 of the turn, then it will come back to where it was. So that's how you can get something with symmetries of a pentagon. What about higher dimensions? So here we can use the same techniques to see something that has symmetries of an icosahedron. So these 2 polyhedra that you can see here, again, sort of nested structure. You have one in the outside and one in the inside. And this way we can see that from projecting from 6 dimensions to 3 dimensions, we can have some sort of nested structures like this, and they have icosahedral symmetry. So yeah, you can see it has like it has some pentagonal things inside here, so we can rotate 1/5 of a turn and it doesn't change. Or you have some sort of triangular things as well. So for instance, this hexagon has symmetries of a triangle, and you can again rotate 1/3 of a turn there. Okay, so this is the example, the one of the things that we want to study. So the symmetries of an icosahedron and how we can see it, how we can use higher dimensions to somehow produce these objects. So many objects have the same symmetries of as an icosahedron. So you can see the polyhedra here. So I just picked 3 pictures of the polyhedra. This is called dodecahedron, icosahedron, and I believe rhombicosahedron. They have complicated names. But you can see that although these look like different pictures, they all have the same symmetry as an icosahedron. But these are just mathematical objects. But there are actually some real-life objects that you can see in your life that have the same symmetries. So, for instance, probably most of you have seen a football. So a football, if you look at how it is arranged, how the black and the white faces are arranged, it also has symmetries of an icosahedron. There are some buildings, some nice buildings. So this one, I believe, is some science museum in Vancouver, which also has the same symmetries as an icosahedron. But what I wanted to study here are mostly viruses. Many viruses have this property that they have the same symmetries. So here you can see again, some pointy things. So it's not exactly an icosahedron, but it has the same symmetry. Okay, so how we can study these things? We do what I said before. We use nested polyhedra. So the example you saw before, it looks like the picture on the right, and on the other hand, on the left, we have some biological object, which is a virus, and it is a bit more complicated. So what do we see in these pictures? Well, we want to match somehow this picture on the left, which is what exactly we have in the real life in biology, with picture on the right, to somehow describe what we see through the microscope, describe it mathematically. So first, we just remove the edges. We keep the points, just the vertices of our polyhedron, and we have some sort of nested structure. So perhaps when we cut it, if we cut things open, we can see better what structures we have. So in biology, again, we have a virus, and the virus has some thickness in here between the outside and the inside. And the nested polyhedra, again, we have some sort of two layers. So what happens, what we do is we try to combine these pictures in a way that we somehow, the outer layer in mathematics describes the outer layer in biology, and the inner layer describes the inner layer. So when we combine these things, we get a picture like this. So here points, these blue and these green points, they just come from our mathematics, from projection from 6 dimensions down to 3 dimensions to have something that we can draw. And in the middle between these green and blue points, we can see the virus, how it looks like. So it is a way to produce nice pictures, but it's also a way to study something, and maybe we can tell more in biology as well. So for the pictures part, I would invite you to see more. There are more pictures like this in the Wunschning Gallery at the Mathematical Institute at the University of Wrocław. So you can see more things, more nice looking pictures, which also have some basis in real life in biology. So this is open for the first half of October. And yeah, and that's everything I wanted to say. So thank you for your attention.